All right, this is the start of the relational database models. We talked a little bit about them last week, and we're going to see how all of this starts to fit together tonight. The key behind all of this is the fact that the better we design the database up front, the better we do the chin diagram or the crowfoot or whatever you get comfortable with using, the better off you're going to be when you actually implement that database. Now, one of the interesting key things or interesting things you all might find out is if you go out and download Visio, and you may have already done that off of your DreamSpark account, then it contains models for Crowfoot and for Chen. So you can do your diagramming should you so desire doing that way. James, welcome. Glad to see you back. Okay, this is going to be the end to a perfect day. We are not advancing our slides. I feel so sorry for Professor Casey when he listens to. Oh, never mind. Okay, we're going to run through, as I said, we're going to run through this kind of fast tonight. The keys that I want you to see are at the end when we talk about the relationships and some guidelines for those. Figure 3-1, a little bit different way to define a rational table. Take a look at that as you go through. Just kind of be comfortable with it. They throw in a new word, tuple or tuple, depending on how you want to pronounce it. Either way is all right with me. And it's a word that you'll hear out there in the database community periodically. But this is table 3-1. They also cover in chapter 3 on table 3.3 and around there primary keys and foreign keys that we talked about earlier in the semester in Oracle, but they've added a couple of new keys that you might want to acquaint yourself with. First is the super key, candidate key we've already talked about, and the secondary key. The databases that we're going to develop are going to be relatively straightforward. So we'll probably have a primary key and a foreign key. And we won't go much further than that. But take a look at these. Just be familiar with the fact that their keys can be called several different names. Relational algebra. This is getting us ready for our adventure with PL/SQL. So we already know about the select statement. The other statements that we have the possibility of getting into are the projection, the join, the intersect, the union, the difference, the product, and the divide. Product and the divide we don't deal with very much. And you want to see that in a lot of databases out in the jungle. But unions, differences, joins, intersects, you'll get to see those. These you may be able to see better in your book, figures 3.6 and 3.7, but it's a very nice graphics display on what happens when you do a union. Now we're going to learn about the code a little bit later, but right now we're learning the theory of unions. And so when we do a union with one table and the other table, what do you see as the result? Pretty much, yeah. Let me get over here where I can get my glasses. Pretty much everything that is in both tables you're going to see. All right, the intersect is a little bit different. Figure 3.7. That was kind of easy. Only the information that appears in both the tables, in this case, Franklin Johnson, appears in both tables. So when we do an intersect of our data, we're going to get just Franklin's name. Now, put your thinking caps on for a second. When would you use a union, and when might you use an intersection? This is audience participation, so I'll wait for you. Very good, DJ. What type of union will we use with that? How about a Rose State College phone book where we use student and faculty? So a union would generate that phone book for us. Charles. Oh, very good. Very good. So if we wanted to look for student and faculty, we could do an intersection and find that out. Very good. All right, difference. So difference runs from one table to another. And what we are doing is we always look at the first table as the table that we want to base the results on, and then the second table is what we'll do the comparison to. So if you look at that, what we are looking at is George, who is not in the second table, Jane, Peter, and Martin. Franklin is all over the place. Okay? So with a difference, whatever our host table is, or our primary table, if you will, we're going to find the entity instances that are not in that second table. So when might we want to use that? You want to clean your list of inactive students. That's a good one. How about if we look at retail? How about if these are all of the people that bought products from us on credit, and these are all the people that had paid us? Ah, so if we do a difference, we're going to find out the slugs that haven't paid us yet. Okay, not slugs, the very nice customers who have not remembered to drop the payment in the mail. We can be PC if we want to. All right, and a product again is something that you're not going to use very often, because what happens is we take this table, and product is the right word, we multiply this table, so we print out everything for every instance that's in both tables. That gets to be huge if you do that with something like a census table. All right, just a quick refresher. Data dictionary, we talked about that. This should not be new to you. System catalog, however, is something that we didn't really discuss in Oracle. And the systems catalog looks specifically at the metadata. It's going to contain some details about the data dictionary and all the objects in the database. You, as a developer, maybe even as a database administrator, will become very, very familiar with the data dictionary. By the way, the DoD data dictionary runs up into the tens of millions of attributes and instances or entities that are defined, and it'll drive you nuts trying to look for it or look through it. I actually found parts for, and this has been a while ago, but I actually found parts for a B-36 bomber that theoretically were still in the inventory. Uh, James was in the Navy. I mean, we've got Navy ships from pre-World War II still around. So think about the database they have to maintain. Uh-huh. do we know anybody that's done that, James? Ah, okay. Yeah. This reminds me of MASH, where Klinger was trying to eat a Jeep to take it home. And, okay, moving on. Systems catalog, up at the higher end of the administrator functions, you're going to get into the systems catalog. You know, us line people, they don't allow to touch that very often. All right, this gets more into what we talked about last week in relationships. Remember, we have a one-to-many relationship. This is the ideal modeling of data that we want to try and achieve. A one-to-many relationship. It makes it a whole lot easier for us to write the queries and make things work. It should be the normal in any relational database design. So as you are designing your databases in your teams, your goal is to strike a one-to-many relationship in everything that you write. Now, that's the goal. Can it be done? Most of the time. There are times when you can't get away from a many-to-many relationship, but we want to strive for the one-to-many. It makes it a whole lot easier to process. One-to-one relationship, very rare. You're designing a database at that time that's going to involve a whole lot more entities than what's needed to create your one-to-one relationship. But there are times when both the many-to-many and the one-to-one relationship is necessary, and we have to use it. The many-many relationship, uh, they say, can't be implemented in a relational model. I like to modify this by saying it can't be implemented very well, if at all, in a model. You can get away with putting it in, but it's going to create some problems for you. DJ. Yes. Yeah. Yeah. And if I tell you, then what am I going to evaluate your team on? The answer is yeah. Work on it a little bit. If you can't get it, then I'll help you with it. But it's possible. It can be done. It gets very messy. All right, when we do a many to many relationship, and to partially answer DJ's question, think of it as peeling the onion back. How far back do we have to peel that onion to get a one-to-one relationship? You look at the data. Drill down is probably a better term to use. You look at that data and you drill down further and further and further until you can set up a one-to-one relationship. We kind of look at that at the last couple of slides in this series. They have some very good diagrams in chapter 3, and it takes our crowfoot of diagramming a couple of steps further. First of all, we go back to our painter. Uh, One and only one painter paints one-to-many paintings. Could a painter paint 0 paintings? Well, yeah, but we probably wouldn't call him a painter then. Okay, call him a carpenter or something. All right, but this is a relational database norm. It's found in most of the database environments. This is the way, this is the goal you want to try and achieve with what you're designing. Okay, a one-to-many. When you start to think about it, sometimes all you have to do is look at your data relationship from a different angle, and the one-to-many relationship will pop up. Now, again, and let me remind you, business rules come into play here, and business rules will come into play in what you are developing. Some of them we will get answered. Some of them, as you're going to find out tonight, you're going to get the answer on your own. All right, but anytime you've got a business rule that's going to impact your relationships, you want to make sure you have that business rule written down somewhere so you can keep track of it. But one-to-many relationship. If we read it backwards, how does it read? Yep. Many paintings are painted by one and only one painter. And the business rule would be only one painter can work on the painting. No co-authorships. One-to-one relationship. One entity related to one and only one other entity, and vice versa. All right, this is where we made the database, we've tried to make the database too perfect. Sometimes means the entity components were not properly defined. Um, I used to see this a lot with some of the people that I worked with over across 29th Street, and they didn't totally understand databasing and how to design relational databases. And bless you. And so you get into that problem. Okay, we're not defining things properly. Could indicate that two entities actually belong in the same table. Where a good example of this is we create an entity called last name, first name, and we want to associate an address with that last name, first name. So we create an entity called street, we create an entity called town, we create an entity called state, we create an entity called zip code. All right, too many entities. We can combine and we can have first name, last name, possibly in an entity, and then we would have the address as another entity with attributes identifying the street and house number, the city, state, and the zip code. So this is where we get into these, where entity components aren't really defined or they actually have been broken out too far in one table. DJ? Oh, you can do that. It depends on how you want to identify or what your data definition is. How you want to define your data. There are some situations, Rose State as an example, where um, I think the way they store student names is student names and IDs. And then from your ID, we can pull your address, we can pull your class schedule, and so on. I would need to verify that, but I believe that's the way our PeopleSoft works. Uh, and in some instances, that works extremely well. In others, it doesn't. It tends to be a speed issue. If I just want to run a list of names and not have to call out or ignore a bunch of data. Sometimes if I've got a table with first name, last name, and a primary key, that table's going to run pretty fast. Okay, so did that help? It depends. Again, we can make generalities about all this, but the real key becomes what's the database designed to do? Is it going to be a data? How often does Rose State, as an example, use your street address? Uh, or mail you something. Anymore, we use zip code. But periodically, they want to have your address, so it's out there. But we don't have to sort through it every time we want to create a list or send you an email. Okay. And again, I can't stress enough, you have to know what the business rules are, how the data is going to be used by the end user as you start to design the database. And then that answers a lot of the questions for you. Okay, if we talk about professor, one and only one professor chairs one and only one department. Makes sense. It's a one-to-one relationship. What are our understandings in this? What would our business rule be? No co-chairs, and what else? You can't chair more than one department. As an example, here at Rose, I'm in three departments right now: CIT, management, and multimedia. So I can be in three departments without any problem. But if they wanted me to be the department chair, I could only be the chair of one of those divisions. And this is a rule we have at Rose also. So just an example of a one-to-one relationship. Implementation by breaking up a set of one-to-one relationships. This is going to avoid problems with the many-to-many relationships that we get into, and the necessity for creating composite entities, which I really don't like. And this includes foreign keys as part of other tables. And remember, a foreign key is always going to refer back to the primary key that it's initiated with. I much prefer a foreign key, the use of foreign keys to composite keys, because I've seen too many times where the use of composite keys in creating additional entities causes a problem. And the relationship in the design works very well because the designers know exactly what they're talking about. But when it gets out into the wild and the end users start to work with it, it can become very possibly very confusing for those end users. So I recommend a primary and a foreign key. Okay, here's our many-to-many relationship. One-to-many students has one-to-many classes. What's the initial problem that you see with this database? Well, very true, Chris. Right on target. There's something else there that this type of relationship could open us up to if we're not careful. Yeah, but before we get to the end user, we could have a class that's no one is enrolled in, or we could start to generate redundant data. And what's our key? One of the first rules we talked about in Oracle: enter the data one time, make sure it's correct, and then stop with it. In this case, to establish the relationship, we'd have to identify in probably this entity some kind of relationship to all the students, and we'd have all the students listed here, so it would be very easy to start slipping data as we go back and forth. So the relationship starts to get a little messy. Data redundancy, data anomalies. We've talked about this before. If you look closely At the database from hell that I showed you last semester, there were actually repeating lines of data. And they would enter uh, a national stock number. Uh, the most I ever caught him was 4 times. The same stock number right there. The first time I asked, what's his name about it? Oh no, that's supposed to be there. Exactly the same data 4 times. Oh yeah, yeah. It's a different part. Come on. No, it's not. Quit trying to kid me. Foreign keys, control data redundancy. We're using attributes. We're sharing attributes from different tables. Using a foreign key, you're not having to re-enter that data a second time and run the risk of making a mistake with it. Sometimes data redundancy is necessary, but if you work with it hard enough, you can usually eliminate it. And it will help you out in the long run. Whoa. Two more things I want to talk about. The first is indexes. And an index we talked about in Oracle just slightly, but this is allowing the database engine to arrange your data in an order that makes it easily accessible for that database engine. Now, the problem behind using indexes is that every time you make a change to the indexed field, it re-indexes all the data in that field. So if we had a table of student IDs or students at Rose State, let's say, and we set the index up on a student ID number, then anytime we added or subtracted or changed, which I assume could maybe be done, a student ID number, that database engine would have to re-index all of that database. And depending on the size of the database, it's going to take a while to do. So indexes are very, very useful in speeding up your database, but the problem is how much data are we talking about? And there are tricks that you can use to get around that indexing by creating what we call mirror tables. And uh, an easy way to do it, let's say that, just to give you an example, let's say that we want to use an index on student IDs. And we want to run through and look at students enrolled in information and technology, anybody that's enrolled there. And every time that we would add a student or take a student out, we'd have to re-index the entire records of all the students at Rose State. Well, one way we could do it is create a mirror table of students using a select table and only include the students in information technology. So that would be a way that we could get around that. Then we're only indexing a subset. It's not affecting that master set until we put the data back in. So it's a workaround. It's a way you can work with it. The other thing that I want to pass along to you tonight, remind you of, is the safest way that you can present data to your end users is through a view. And a view protects the origin and exactly what data you have stored in your database. Because how's a view created? Anybody remember? Not the code, but the theory behind it. Shows you so much of what of the data that you've collected, right? So we go back to our student example. If we want to take a look at um, students at Rose State, and all we want the professors to see is the student ID, the student name, and the year that student is at Rose, freshman, sophomore, super sophomore, galaxy sophomore, whatever that is, however high we go, then we can create a view that only showed that data. And our professors would have no clue what other data we have available on the students. So, especially out there in the jungle, it is very, very wise to protect your data from, we used to say, prying eyes of your employees, but we can work on that. Okay, that's it for chapter 3. It expands on what we looked at in the Chin diagram, run through it. We're going to start to apply this stuff probably Thursday night because Houston, we have a problem with our two database, or with our project. And it was pointed out to me this morning. Why don't you take a 15-minute break and we're going to come back. I'll explain what's going on and we'll divide into teams and see how we're going to handle the problem. And if you get back early, we'll start early.